Section 9.3. Let us denote by n of A the number of elements in A. Theorem number 1. Suppose a finite set A equals the union of k distinct, mutually disjoint subsets, A1, A2, and so on, AK. Then the number of elements in A is the number of elements in A1 plus the number of elements in A2 plus and so on, plus the number of elements in AK. So theorem 1 is pretty obvious. But now please take a look at theorem 2 and theorem 3. If A is a finite set and B is a subset of A, then the number of elements in A minus B is the number of elements in A minus the number of elements in B. Well, to explain why this works, let us go back to section 6.1. Please take a look at this Venn diagram. So here B is a subset of A. It's exactly what is written here. B is a subset of A. The number of elements in A minus B will be this region. Is the number of elements in the whole A minus the number of elements in B. It's exactly what is written here. Lastly, the number of elements in A union B is the number of elements in A plus the number of elements in B minus the number of elements in the intersection. Now let us go back to Venn diagrams. We are talking about the union. Here is the union, the whole shaded region. In order to find the number of elements in this region, we add the number of elements in A, the number of elements in B, but note that over here we will count elements twice. Therefore, we have to subtract the number of elements in the intersection. It's exactly what is written here. Now, we can generalize this formula to the case of 3 sets. The number of elements in A union B union C is the number of elements in A plus the number of elements in B plus the number of elements in C minus the number of elements in A intersection B, A intersection C, B intersection C, and then plus the number of elements in A intersection B intersection C. Let us discuss examples. A code word consists of 1 to 3 letters chosen from the 26 in the alphabet with repetitions allowed. How many different code words are possible? So we use theorem 1. This. The total number of code words equals the total number of code words of length 1 plus the number of code words of length 2 plus the number of code words of length 3. Now, by the multiplication rule, the number of code words of length 3 is 26 times 26 times 26. Over here, 26 times 26, and of course, the number of code words of length 1 is just 26. Here is the answer. Next, how many integers from 1 through 999 do not have any repeated digits? Again, we start with theorem 1. The number of integers from 1 to 999 with no repeated digits equals number of integers from 1 through 9 with no repeated digits plus number of integers from 10 through 99 with no repeated digits, plus the number of integers from 100 through 999 with no repeated digits. Now let us count the number of elements here, here, and here. In each case, we use the multiplication rule. But folks, who can explain me why all of a sudden we have 9 times, again 9 times 8? Anybody?
Is it because in 100 you have 2 zeros as opposed to 1 in 10 where you only have 1 zero?
So can you tell me why we have 9 over here, not 10?
You can't start with a 0?
Exactly. Remember, we are talking about 3-digit numbers. A 3-digit number cannot start from 0. Therefore, for position number 1, we have only 9 possibilities from 1 to 9. Can you tell me why do we have 9 here again?
Because now you can use the first digit, but you can also use 0, so it's the same number.
Exactly. Because out of 10 possible digits from 0 to 9, we can use 0, but we cannot use the digit which is on position number 1. Therefore, 9 is the following: 10 possible digits minus 1, which is already taken. The answer is 9. Anybody, why do we have here 8?
Because now we can't use the first digit and second digit.
Exactly, because again, the total number of digits is 10. 1 digit is taken here. Another digit is taken here. So 10 minus 2, 8. Now let us go back to this. For the same reason, position number 1 can be anything except for 0. Therefore, we have 10 minus 1 possibilities, 9. Here we have again 10 minus 1 possibilities because we can use 0, but we cannot use the digit which is on position number 1. So it's 10 minus 1 again, which is 9. And here it's pretty obvious. We have 9 possibilities because we cannot use 0. The total number of integers is this. Now, to answer 3, we use theorem 2. Please take a look at this. How many integers from 1 through 999 have at least 1 repeated digit? So instead of counting the number of integers that have 1 repeated digit, 2 repeated digits, 3 repeated digits, we apply theorem 2. By theorem 2, the number of integers from 1 through 999 with at least 1 repeated digit equals the total number of integers from 1 through 999 minus the number of integers with no repeated digits, which is 738 by the previous exercise. So the answer, 999, which is over here, minus 738, which is over here. Next, how many integers from 1 through 1000 are multiples of 3 or multiples of 5? Now let us use theorem 3. Let A be the set of all integers from 1 through 1000 that are multiples of 3. B are multiples of 5. Please take a look at what is the union of these sets. A union B is the set of all integers that are multiples of either 3 or 5, or both. The intersection is the set of all integers that are multiples of 3 and 5, which means A intersection B is the set of all integers that are multiples of 15. Now, let us use the formula from theorem 3. The number of elements in the union, it's exactly what we need, is the number of elements in A plus the number of elements in B minus the number of elements in the intersection. Question is, how do we find, say, the number of integers from 1 through 1000 that are multiples of 3? Here, let us use the floor function. And by brackets, we mean floor function. So we divide 1000 by 3 and take the floor function. The answer is 333. This is the number of integers from 1 through 1000 that are multiples of 3. Similarly, we have 200 multiples of 5 and 66 multiples of 15. We put pieces together. Here is the answer. By the way, you may ask me a question, why in the world here we use the floor function? Well, let me give you an example. Say, let us consider integers not from 1 to 1000, but say from 1 to 9. It is easy to count the number of multiples of 3. These are 3, 6, 9. So we have 3 multiples of 3. And indeed, 9 divided by 3 is 3. Now, let us count the number of multiples of 3 from 1 to 10. Of course, we have same number of multiples of 3. It's again 3, 6, and 9. Note that the floor function of 10 divided by 3 is again 3. Now, let us replace 10 by 11. How many multiples of 3 are there from 1 through 11? Again, it's 3. And indeed, floor function of 11 divided by 3 is still 3. However, if we replace 11 by 12 and find the number of multiples of 3 from 1 through 12, now these are 3, 6, 9, 12, 4 numbers, and indeed the floor function of 12 by 3 is 4. One last time, any questions?
If A was a set from 0 to 1000, would 0 be considered a multiple?
Yes. So if we include 0, then the number of multiples of 3 from 0 to 1000 will be 334, because 0 is a multiple of 3. Next. Okay, guys, let us do these exercises together. How many arrangements of no more than 3 letters can be formed using the letters of the word network with repetitions allowed, no repetitions allowed? What do you think?
7 times 7.
So, first of all, we use theorem 1, correct? No more than 3 letters means 1 letter 2 letters, 3 letters. So if we have one letter word, since all letters are different here, and the total number of letters is 7, the number of one letter words will be 7, correct?
Yes.
Yes. Now, how many 2 letters words?
I didn't do it this way.
Okay.
I thought it as we have 3 places. In first place, we can have 7 digits. In second place, we can have 7 digits. And in third place, we can.
Give me a second. It's written no more than 3 letters, not exactly 3 letters.
Oh, okay.
You see it?
I have an idea.
Yes. Anybody else?
I have an idea.
Yes.
So first you would need to count just like N, E, T, 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 which of those you have 7. Then you have to add the permutation of 7 permutation 0, 7 permutation 1, 7, or sorry, if there, I don't know if there's 7 permutation 0, but you just go 7 permutation 0, 7 plus 7 permutation 1, 2, and 3.
Why are you talking about permutations? In permutations, repetitions are not allowed.
Oh, okay, then it would be
Repetitions are allowed.
okay, so it would be combination then.
So let us split this problem into 3 pieces. Here it says no more than 3 letters. No more than 3 letters means 1 letter, 2 letters, 3 letters. Let us start with 1 letter. How many 1 letter words can be formed from these letters?
Oh, 7? Right, yeah.
7. How many 2 letters words?
It would be 7 choose 2.
We don't really need choose. We did not discuss choose yet. Here it's written, repetitions allowed. So we have 2 positions. In position number 1, we can use any of these 7 letters. In position number 2, we can use again any of these 7 letters.
Oh, so it's 49 then.
7 times 7, multiplication rule. Is this clear?
Yeah, yes, yeah.
Since repetitions are allowed, we use the multiplication rule. Now, how many 3 letters words can be formed?
That would be 7 cubed. Then.
7 times 7 times 7. Now, what is the final answer for A?
399, I believe.
399 means, why do we have 399?
That's 7 plus 7 times 7 plus 7 times 7 times 7.
Exactly. It's the final answer is 7 plus 7 square plus 7 cube. Okay, 1B. Can anybody help me with 1B? No repetitions allowed. Again, we have 3 cases. 1 letter word, 2 letters word, 3 letters word.
For 1 letter, it would be 7.
For 1 letter words, we have 7 possibilities. For
And
2 letters words,
it would be 7 times 6.
7 times 6. Because in position number 1, we can use any of these 7 letters. But once 1 letter is taken, we can use only 6 remaining letters for position number 2. And by the multiplication rule, 7 times 6. Lastly, 3 letters words. How many possibilities?
7 times 6 times 5.
7 times 6 times 5. Absolutely. Now, the total number of words is
7 plus 42.
7 plus 7 times 6 plus 7 times 6 times 5. Okay, number 2. How many ways can the letters of the word quick be arranged in a row if the Q and the U must remain next to each other in the order QU?
You can just think QU as one element instead of two. So
Okay.
basically you have 4 slots, and for each one, like this 4, it's 4 times 3 times 2 times 1.
Which means 4 factorial, correct?
Yes.
Exactly. So we think about QU as about a single object. We have object number 1, QU, object number 2, I, object number 3, C, object number 4, K. We have 4 different objects. In how many ways we can rearrange 4 different objects? In 4 factorial ways. To be, how many ways can the letters of the word quick be arranged in a row if the letters QU must remain together, but maybe in either the order QU or the order? Guys, I have to update. What I mean is the order QU or the order UQ. How would you answer this question?
So for QU, you have factorial ways to put them together, but
Yes.
for Q, you also have 4 factorials, because you can also treat that UQ as one element.
Yes,
And
which means
it's 4 factorial times 2.
yes, it's 4 factorial times 2. 4 factorial for QU and 4 factorial for UQ. How about 3A? A group of 8 people are attending the movies together. 2 of the 8 insist on sitting together. In how many ways can the 8 be seated in a row? Any ideas?
7 factorial times 2.
7 factorial times 2, absolutely. Because we think about these 2 people as one object, so we have, instead of 8, 7 different objects. But it does not matter. We have person number 1, person number 2, or person number 2, person number 1. The order does not matter. So similar to 2b, we have 7 factorial plus 7 factorial, which is 2 times 7 factorial. How about 3b? 2 of the people do not like each other and do not want to sit side by side. Now, how many ways can the 8 people be seated in a row? How do we do this?
8 factorial minus 2 times 7 factorial by difference rule.
Exactly, we use the difference rule. 8 factorial, the number of rearrangements of 8 people minus the answer for A, 2 times 7 factorial.